So here's question 4 from the homework. Find the length of each vector and the angle that it forms with the positive x-axis, x1 axis, meaning the x-axis, measured counterclockwise in degrees, which is the usual direction. So here's what our situation is. Here's my positive x-axis, or x1 axis if you really like. I guess you could call this x2. That seems silly, but I get it. I like to hear it. Okay, I guess. So we want to find, for example, the length of this vector and also the angle it makes with the positive x-axis. A equal to -6, 0. Okay, well, so the nice thing about a vector with only one non-zero component is you already know its length. We know the magnitude of A is just 6, right? We went right, that point there, that's the end of the vector, is the point -6, 0. We went 6 in one direction and 0 in the other direction, so the length is 6. You could also calculate it. And you can say, okay, fine, it's the square root of -6 squared plus 0 squared. And I think you guys can see, right, when only one of the things is not 0, you're only going to get that number squared, and then the square root of that is just going to be the positive, the absolute value of what you started with. So that's going to be +6. Okay, the angle is a little bit more work, but although not really in this case. So for this particular one, I think we can just eyeball it, right? If you're saying I'm starting here in the positive x-axis direction and then going counterclockwise over to here, what angle is that? It's 180 degrees. I do think it's worthwhile, though, to at least think about how you would show the work. So if I want to find the angle between, oh, what's my other vector? How do I find the angle between two vectors? Well, I guess I should really ask, I have to have another vector, right? Because we can only find the angle between two vectors. So the thing is, this vector in the positive x-axis direction, we should just make up something. You can pick anything you wanted. You can pick 1, 0, or 2, 0, or 3, 0, or anything comma 0. Right? If you want a vector going this way, it's got to be, I'm going to call it, I don't know, I guess I'll call it x. It's got to be anything comma 0. It's probably going to be easiest to pick 1 comma 0. Okay, and now we're going to find the angle between the two vectors using the usual calculation. My preferred way of writing it is to write cosine of the angle is the dot product of your vectors. So the dot product is, so it's this vector dotted with this vector, or I should say that vector dotted with that vector. So A dot x divided by the magnitude of A times the magnitude of x. Okay, let's see. A is -6, 0, x is 1, 0. So the dot product is -6 times 1 plus 0 times 0. The magnitude of A is 6. The magnitude of x is 1. So look what we get. We get -6 over 6, which is -1. So cosine theta equals -1, which means theta equals the inverse cosine of -1. Or you could just say theta is the angle whose cosine is equal to -1, and that angle is 180 degrees, or pi radians. Either way you want to say it. Although the question does ask for the angle in degrees, so we should say 180 degrees. Okay, we'll do the next one. Now, I like these questions in your book because they are or in the homework, because they're definitely the types of angle questions I would ask, where the angle actually ends up being a nice angle that we should be able to find without using a calculator. So I wouldn't be surprised if on your final exam, there might be a question where you had to find an angle between two vectors without using a calculator, and the angle was something like 45 degrees, or 30 degrees, or 60 degrees, or 90 degrees, or something where 90 degrees should be easy because the dot product should be 0. But let's look at this next one. So now the question is, I want to find the angle between the x-axis, which I'm going to say, oh yeah, the x-axis, I should really say the positive x-axis, which is, again, you can use any vector where the second component is 0. It's going to be easiest to use the vector 1, 0. And then they're giving us the vector, what are they giving us here? Negative 4, negative 4, comma 4. And they're calling that B. Okay, well, first we need to find the length of this. The magnitude of B is, again, just the square root of the components squared and added together, which is going to be the square root of what, 16 plus 16, which is the square root of 32, or I would probably write it as the square root of 16 times 2, because then the square root of 16 is 4. So this is 4 square root of 2. So that's how we can find the magnitude. Again, the magnitude, at this point, the magnitude of a vector should be a pretty straightforward calculation for all of you. You're just taking all the components, squaring it, adding it together, and then taking the square root of that. That's it, every time, every time. Yeah. To find the angle, again, I'm going to say that cosine of my angle is the dot product b dot x divided by the magnitude of b times the magnitude of x. That's the other reason you want to find the magnitude first, is because it comes up in your angle equation anyway. So let's see. B dotted with x is going to be negative 4 times 1 plus 4 times 0. So negative 4. And the magnitudes are both positive. Magnitude is always positive. So the magnitude of b times the magnitude of x is going to be 4 root 2 times 1. And we'll point out, before we even do anything else, that since this value is negative, we know that cosine is negative, not in the first quadrant, right? Cosine of an angle between 0 and 90 degrees is positive, but an angle in the second quadrant between 90 degrees and 180 degrees. So we know that our angle here, since it's going to equal a negative number, has to be an obtuse angle, bigger than 90, less than 180. So let's see here. We can simplify this. We get that cosine of theta is equal to the 4's cancel, and you get negative 1 over root 2, which is fine to write it that way, but you might prefer or be more familiar with writing it as cosine theta equals negative root 2 over 2. I know that cosine of 45 degrees is positive root 2 over 2, so I need the supplemental angle in the second quadrant, which is 135 degrees. So theta is the inverse cosine of negative root 2 over 2, which is indeed 135 degrees. Okay, let's look at this last one. So yeah, these are all set up in such a way that so yeah, if you're trying to find the angle that a vector makes with a specific axis, just use the unit vector for that axis. So if the question was instead like what angle, so the next vector is, c equal to 5 root 3 negative 5, which is going, like over and down. Maybe it's going to like right like that. Oh, this is a good question. I like this question. This one is tricky. But I just want to point out, right? So if we're trying to find the angle that this vector makes with the x-axis, right, we want to use the vector x equal to 1, 0. But if someone said like find the angle it makes with the y-axis, then you'd want to use the vector that goes in the y direction, which would be like 0, 1. Or if they said the negative y-axis, 0, negative 1. So any axis you're given, just use the appropriate unit vector. Usually we measure angles from the positive x-axis, but someone could write the question differently. All right, so same process. What's the magnitude of c? The magnitude of c is the square root of, 5 root 3 squared plus negative 5 squared. So let's see, that's going to be 5 squared is 25. Square root of 3 squared is 3. Plus negative 5 squared is 25. 3 times 25 is 75. 75 plus 25 is 100. So you get the square root of 100, which is 10. That's nice. So the magnitude of c is 10. And then the cosine of the angle. This is interesting. Let me read this question again. Let's be careful here. Find the length of each vector and the angle that it forms with the positive x-axis measured clockwise in degrees. Okay. So you count for here. No. Sorry, there's a little bit of a chocolate chip on my. Sorry, I was having a cookie earlier. A little bit of chocolate chip on my lips there. Sorry. Anyway, excuse me. Cosine of theta is equal to dot product. So c dot x divided by the magnitude of c, magnitude of x. So we're going to get, a positive result. Positive? Yeah, okay. Did I draw this right? I did, right? Over and down, okay. So let's see what happens. Oh yeah, of course. Positive because it's in the fourth quadrant. So let's see here. So we do this. C dotted with x is going to be 5 root 3 dotted with 1. So you're going to, 5 root 3 times 1. So you're going to get 5 root 3 over magnitude of c times magnitude of x. This reduces to 5 over 10 reduces to 1 over 2, so you get root 3 over 2, which is an angle, I'm sure, or a value that we're used to seeing. So cosine of our angle is root 3 over 2. So here's the thing, and this problem is definitely meant to kind of, I don't want to say it's like meant to like mess you up if you're using a calculator, but it's definitely meant to kind of make sure that you are understanding what's really happening here. Because if you use a calculator, you're going to get the wrong answer. So if you use a calculator, the inverse cosine of root 3 over 2 on a calculator is 30 degrees. Because cosine of 30 degrees is root 3 over 2. The problem is this angle definitely measures. So if we read the question again, it says, right, find the angle that is formed with the positive x-axis measured counterclockwise in degrees. So to start here, we have to go all the way around here. So this angle is 30 degrees. It's our reference angle. This angle is 330 degrees, right? It's a full 360 minus 30. That's a little tricky. So our angle here is actually 330 degrees. Interesting. So I should say, when you find the inverse cosine of a value, it'll always spit out a value that is between 0 degrees and 180 degrees. But depending on the context of your question, your angle might actually be anything between 0 and 360. Or it could even be negative, right? Someone could have said, what's the angle? And you say, oh, that's negative 30 degrees would also be a correct answer if it was phrased differently. But yeah, be a little bit careful with those, depending on how they're posed. Okay, that's all I've got about that one, unless there's any questions. Actually, the other side of the board's erased here. It is not. Hopefully you guys are doing all right. This matrix stuff hopefully isn't too bad. Like it's the calculations you have to do are pretty not too terrible. But let me ask this question, and let me ask you guys if this looks familiar or if I'm crazy and somehow took it from one of my other classes. I don't think I did, but you never know. So the question was to find I believe the equation of the plane through the point 3, 2, 5. And perpendicular to the vector. Let's give the name -5, 6, -1 equal to, call it n, because that's typically what we call a perpendicular normal vector. Does this look familiar, or am I off? Am I out of it? Am I losing it somehow? Let's check. Guys are like, maybe. Let me just look and see. I think somebody asked this question, but now I feel like I should double check. sorry. Okay. No, close that one. It looks familiar. Okay. I mean, I thought so, but I wasn't positive because I wrote it down, but then, I got distracted writing down a million other things. Yes, somebody from this class definitely did ask. Okay, good. So let's take a look at it. So there's a lot of explanation that goes with a problem like this, but the calculation is actually really, really easy. So here's the deal. If you've got, so let me show you the easy way, and then let me do the explaining afterwards. So we've got a plane, right? And you've got this vector sticking out of it, and this vector is perpendicular to the plane. And this vector here, -5, 6, -1, equal to the normal vector, n for normal. Again, just in case you guys don't remember or I haven't said it enough times, perpendicular, normal, orthogonal all kind of mean the same thing, meaning they're perpendicular. So here's the very easy way to find it. These components of your vector correspond to or are the coefficients of your variables in your plane equation. So I can immediately say, okay, I know my plane equation is going to be -5x plus 6y minus 1z equal to a constant. Great. So it's kind of like the point slope form of a line where you say, okay, I know y equals like 6x plus b, and then you have to find the b part. To find the b part, you plug in the point you know it goes through. So plug in the point you know it goes through, and then solve for the constant. So I plug in 3, 2, 5, I get -5 times 3 plus 6 times 2 minus 1 times 5 equal to d. So see, -15 plus 12 minus 5, that's going to equal -8. So that's what d is going to equal. Okay, so then that tells us that the equation of our plane is -5x plus 6y. I'm going to write minus z instead of minus 1z. Sounds like I'm saying 1z, like the things you put on that have a little footy pajamas. Yeah, okay. 1z, that's what, yeah, right? Yeah. Oh, sorry. -5x plus 6y minus z equals -8. And that's how you get the equation of a plane when you know a point that goes through and a vector that is perpendicular to it. And it's pretty not terrible once you know how to do it, right? It's like, oh yeah, normal vector, all right. Let me explain why it works, just very, very briefly. Unless, well, no, I should, yeah. So just in case you've forgotten how this works, the way this works is you're basically saying, well, let's pretend this here is some point x, y, z in the plane. This is still your normal vector, -5, 6, 1, -1. And this is the point that we know the plane includes, which is the point 3, 2, 5. Well, the way this works, you can say this vector, let's call it PQ. PQ, which is in the plane, is perpendicular to the vector n. Okay, we know something about perpendicular vectors. We know their dot product is equal to 0. So this vector PQ, which is the q coordinates minus the p coordinates. So I'm actually going to write this slightly backwards though. I'm going to write it as n is perpendicular to PQ. That's the nicer way, but it's not a big deal, but it's going to make it look just a tiny bit nicer. So the vector n, -5, 6, -1, dotted with the vector PQ, which is, let's see, the x coordinate is x minus 3, the y coordinate is y minus 2, and the z coordinate is z minus 5. Since the vectors are perpendicular, their dot product has to equal 0. But look what happens when I write the dot product. It's going to be -5 times x minus 3 plus 6 times y minus 2 plus -1 times z minus 5 equal to 0. And if I multiply this all out, which I've kind of run out of room, let me go up here. I multiply this out, I get negative 5x plus 15. You get 6y minus 12. I get negative z plus 5 equal to 0. And 15 plus 5 minus 12 is 8. So I get negative 5x plus 6y minus z plus 8 equals 0. Or, subtracting 8 from both sides, negative 5x plus 6y minus z equals negative 8. Same equation. So you don't want to do it this long way because it takes more time. But the long way is the reason why it works. Because when you say, oh, if you've got a normal vector, the dot product of the normal vector and any vector that's in the plane, starting at the point we know, going to any point x, y, z, that dot product is 0, which ends up giving you the coordinates of the normal vector as the coefficients of x, y, and z. So we just jump to that and say, okay, solve for d. So that's how you do a question like that. Again, the short way, just say, okay, great. Negative 5x plus 6y minus 1z equals constant. Plug in your point, which is 325, and solve for the constant. Those are good problems because once you know why they work, it's like, oh yeah, of course it's going to be just like do this thing. But if you don't remember why it works, it's kind of like, I think you get the coefficients by using the coordinates of the vector, but I don't exactly remember why that's true. All right. Let's talk about determinants and inverses and all that good stuff. So, determinants and inverses. I thought Professor Burke did a really good job of explaining like when a matrix is invertible, just like how when a number is invertible. Right? She was talking about how if you're going to try and solve like the equation 3x equal to 5, you multiply both sides by the inverse of 3, which is 1/3. So you get x equal to 5/3. This seems smart. And then if you're trying to solve something like 0x equal to 5, there's no solution because 0 is not invertible. You can't multiply by 1 over 0. So matrices, well, actually, let's say we're going to limit ourselves almost exclusively to 2x2 matrices. So I'm going to say the matrix A, very generally, we can either write it as A, B, C, D, which is kind of nice, right? If it's just 2x2, it's kind of easier to write it that way. But some people like to write it as using the nice subscript notation, A11, A12, A21, A22. In either case, the determinant of a matrix, of a 2x2 matrix, is the product of the diagonals minus the product of the off diagonals. The one thing I will say about this is just be careful about negative signs, right? It can be, well, in fact, we'll do a couple examples in a second. I'll just say it there. Or you could also write it as determinant of A is A11, A22 minus A12 times A21. Either way, same equation, just different names for the entries. So this is this is going to be a calculation you're going to do a lot in 17C. Like you're going to just get, it's going to be like second nature to you. You're going to do it so many times. So for example, if my matrix is, I don't know, 1, -5, 2, -2, 6, what's the determinant of A? Well, the determinant of A is 1 times 6 minus -5 times -2. So be careful, right? It can be easy to kind of get the signs wrong if you're not being super careful. So it's going to be 6 minus 10, which is -4. When you do this for a while, you kind of get used to be like, okay, it's going to be 6 minus 10, right? Because it's this product minus that product. Or we could do something, you know, like let's say our matrix was B equal to, I don't know, -7, -3, -4, 2. Why not? Okay, so now let's see. Our determinant of B is going to be -7 times -3, so positive 21 minus -4 times 2, -8. So it's 21 plus 8, which is 29. Something to recognize. In fact, let's look at this matrix. Let's look at the matrix C equal. Let's throw some fractions in there. Something crazy like, I don't know, 1/3, comma, I'm trying to make up something that's going to be not terrible, comma, -2/5, and 1/6, comma, -1/5. Something to observe. In fact, we'll look at both of these. We'll look at this one and we'll also look at this one. D equal to, I don't know, 7, 5, 21, 15. So I want to find the determinant of C. It's going to be 1/3 times -1/5 minus -2/5 times 1/6. Okay, 1/3 times -1/5 is -1/15, and -2/5 times 1/6 is -2/30, which is -1/15. So it's minus -1/15. -1/15 plus 1/15 is 0. This matrix is also going to have a determinant of 0. And the way you can see this without actually doing the work, although you should do the work, but you can see that this matrix is going to have a 0 determinant because it's got, well, both for a 2 by 2, the rows and the columns. This row is a multiple of that row. This row times 3 is that. Or this column is a multiple of this column. It's a less nice multiple, but if you multiply this by 7/5, 5 times 7/5 is 7, 15 times 7/5 is 21. So when the rows of a 2 by 2 matrix are multiples of each other, or the columns are multiples of each other, the determinant is going to be 0. Check it out. Determinant of D is 7 times 15 minus 5 times 21. 7 times 15 is 70 plus 35, which is 105. 21 times 5 is 20 times 5, which is 100, plus another 1 times 5, so 105. Oh yeah, that's 0. The same thing is true here. These rows are multiples of each other. This second row is the first row times 1/2. 1/2 times 1/3 is 1/6. 1/2 times -2/5 is -1/5. So the picture I'm trying to paint for you is that if you notice the rows are multiples of each other, you automatically know that the determinant is going to be 0. Which is kind of cool. Okay, so we know also things about the matrix being invertible. So if your matrix A is equal to a general A, B, C, D, then not the determinant, the inverse of A inverse is 1 over the determinant of A. That's why the determinant has to be non-zero for the matrix to be invertible, because you have to be able to divide by the determinant. If you can't, it doesn't work. And then the way I always remember this, and this only works for 2 by 2s, it doesn't work for anything else. For 2 by 2 matrices, to find the inverse, you switch the diagonal elements and you change the signs of the off diagonal elements. Always works for a 2 by 2. It's kind of nice. So for example, if your matrix A was, I don't know, say something like 7, 3, -2, 1. Sure, that'll be fine. Then A inverse, without even doing any work, I'm going to switch the diagonals. And the off diagonals stay in the same place, but their sign changes. So that's going to be a -3, and that's going to be a +2. Oh, but I forgot something. I forgot the determinant. So it's going to be 1 over, let's see, the determinant is 7 minus negative 6. So it's going to be 13. And we can check that these two matrices are inverses by multiplying them together. So that's the thing, is when you multiply a matrix by its inverse, you should end up with the identity matrix. So let's do a double check. A times A inverse is equal to, so let's see, it's going to be 7, 3, negative 2, 1 times 1. Sure. I'm going to show you guys something as well that I think is worthwhile. 1/13, 1 negative 327. So when you multiply matrices together and there's a scalar multiple, right, that 1/13, it can kind of move anywhere. I'm going to put it in front. I'm going to write this as 1/13 times, now let's just do the matrix multiplication. So it's going to be this row dotted with this column. So 7 times 1 plus 3 times 2, which is 13, or 7 plus 6. First row dotted with the second column, 7 times negative 3 plus 3 times 7, that's 0, right? It's 21 minus 21. And then second row, first column, negative 2 times 1 plus 1 times 2, again, 0. And then negative 2 times negative 3 is 6, plus 1 times 7 is 6 plus 7 is 13. And then the 1/13 times this is going to give you exactly 1, 0, 0, 1. The 2 by 2 identity matrix. So we can see that when we multiply these two matrices together, we do in fact get the identity matrix, which does mean they are inverses. So you want to get very comfortable saying that matrices are inverses. See, what else do I want to say here? Oh, I know, I had a good question. So, yeah. We can also use inverses to solve systems of equations. And I feel like I had some problems there. I hid for myself somewhere. Anyway, let's look at this. So let's say I want to, I want to solve the following system. Solve, what do we got here? 2x plus y equal to 7 and x plus 3y equal to 4. Now I will fully admit you could solve this the old school way, right? You could isolate x, I say x equals 4 minus 3y, plug it in for x up here, get some equation with just y's and then solve for y, plug it back in down here and solve for x. That is not the intent. The intent is to use matrices because, one, sure, it's fine if you've got 2 equations and 2 unknowns, right? It's pretty easy to solve for x and y. But if you have 4 equations and 4 unknowns, or 5 or 6, or many, many equations and many unknowns, it becomes very, very challenging to solve the system without using a more kind of systematic approach, meaning using matrices. So we're going to rewrite this as the matrix equation. So the matrix, the 2 by 2 matrix, is what we call the coefficient matrix. It just has the coefficients of x and y. They do have to be in order, meaning you have to have all the x coefficients in the first column, all the y coefficients in the second column, and so on and so forth. Then we're multiplying it times the vector xy, and it's going to equal the vector 7, 4. Right? If we read this, it makes sense. 2 times x plus 1 times y equals 7. That's the first equation. 1 times x plus 3 times y equals 4. That's the second equation. But you do have to have all of the coefficients for the same variable in the same column. So just to kind of point that out, if someone did something kind of crazy and said, I want you to write this as a matrix, right? They said my equation was x plus 2z minus 3y equal to 1, and y plus 2x minus 5z equals 7, and z minus y minus x equals 9. Before you could do anything, you don't have to, but you would want to rewrite this so that the x's were first, the y's were second, and the z's were third. So that you would rewrite this as x minus 3y plus 2z equal to 1, and 2x plus y minus 5z equal to 7, and negative x minus y plus z equal to 9. And then you can write it as a matrix equation where the coefficients are 1, -3, 2, 2, 1, -5, -1, -1, 1, times the x, y, z variable vector equal to 179. Right, because this matrix equation represents the system of equations, right? What we're really saying is 1 times x plus -3 times y plus 2 times z equals 1, which is exactly the first equation here, and so on and so forth. So just want to point out, right, like if you are going to write a system of equations as a matrix equation, you have to make sure your variables are all in the same order. Okay, to solve this, so if you were trying to solve, and I know she kind of talked about this already, right? If you were trying to solve 3x equal to 5, you would multiply both sides by 1/3. Well, if we're going to solve this matrix times x equal to this value here, we're going to multiply both sides by the inverse matrix. If it exists, which it does in this case. And so if you're trying to solve a times a vector x equal to a vector b, one way to solve it, if a is invertible, is to multiply both sides by a inverse. Just like we multiplied, I didn't even show the work here. Just like we multiply both sides by 1/3 here. So you get x equal to 1/3 times 5. Right, it's the very same idea that you're going to multiply both sides by the inverse. Because they're really, so I should say, multiplying by the inverse of a matrix is essentially the closest thing we've got to dividing by a matrix. You can't say A divided by B, but you can say B inverse times A and achieve a similar result if B is invertible. It's not invertible, can't do it. Okay, so A inverse times AX is equal to A inverse times B. A inverse times A, whenever you multiply a matrix by its inverse, you get the identity matrix. So you're going to get the identity matrix times X equal to A inverse times B. But we know that the identity matrix times any other matrix is just the other matrix, right? The identity matrix is like multiplying by 1. So we're just getting X equal to A inverse times B. So we're going to do that here. We're going to multiply both sides by the inverse. So the inverse of this matrix, let's see. I'm going to switch the diagonals, and the off diagonals get change signs. I also have to have 1 over the determinant, which the determinant is 2 times 3 minus 1 times 1. That's 5. 6 minus 1. And then we're going to multiply this on the other side. So 1/5 times 3, -1, -1, 2, 7, 4. Okay. This thing here is the identity matrix. We don't really have to show it. We could, right? This is going to be, I guess I will show it for the sake of it. So you get the 1/5 out here, and then 6 minus 1 is 5. And then this with this is 3 minus 3 is 0. And then this with this is -2 plus 2 is 0. And this with this is -1 plus 6 is 5. More important multiplication is to do over here. So we're actually going to multiply this out as well. We're going to get 1/5 times, see, 3 times 7 plus -1 times 4 is 21 plus -4 is 17. And -1 times 7 plus 2 times 4 is -7 plus 8, which is -1. Sorry, -7 plus 8 is +1. This is the identity matrix. The identity matrix times xy is just xy. So we get xy equal to 17/5, 1/5. And that is your solution. Your solution here is x equal to 17/5, y equal to 1/5. You can check it, but there's no need. But if you do check it, you get 2 times 17/5, which is 34/5, plus 1/5 is 35/5, which is 7. And then 17/5 plus 3 times 1/5 is 17/5 plus 3/5, which is 20/5, which is 4. Totally works. Let's see, what else do I want to say here? There was another cool problem that I had that seemed worth looking at. It's 255, huh? Okay. Let's see here. What else can we do? I guess we should talk briefly about. Yeah, so let's just do this and we'll call it a day. So let's look at these two systems of equations, which are similar but different. 2x plus y equal to 7, and 2x plus y equal to 5. So it might be pretty obvious here that this system of equation has no solutions. Why? Well, 2x plus y is always the same, right? 2x plus y, 2x plus y. If you pick an x and a y, these two things will be the same. They can't be different values, right? Like if x is 3 and y is 1, well, 3, 1 is a solution here, not a solution here. So this has no solution. And the reason here is because, well, one of the reasons is because the matrix is not invertible, right? If you look at the matrix equation, you've got 2, 1, 2, 1, xy equal to 7, 5. This matrix can't be inverted, right? It's determinant of, if you call this matrix A, the determinant of A is 0, which means it's not invertible. Also, something about the naming here that I think is nice that I've come up with myself. If a matrix has a determinant that's blah. If a matrix has a determinant that's 0, it's not invertible. We also use the word singular. And the way I kind of think about it is a matrix that is singular is single. It doesn't have an inverse to pair with it. Whereas this matrix has a determinant that's not 0, right? Its determinant was 5. This matrix is non-singular. It is not single. It has an inverse to pair with it. So non-singular matrices have inverses. They have a partner. They're not single. Whereas singular matrices are all alone in the world. They are single. They do not have an inverse to go with them to multiply to data identity. So that hopefully will help you remember which is which, because it can be a little confusing that non-singular means you are invertible and that singular means you are not invertible. Okay, but then we can also look at the equation very similarly. Let's change that a little bit. Let's say we had 2x plus y equal to 7 and 4x plus 2y equal to 14. So this is not that different. We have the equation 2, 1, 4, 2 times x, y equal to 7, 14. This matrix, let's call it B. This matrix still is singular, right? Its determinant is 0. It does not have an inverse to go with it. It's single. But in this case, there's an infinite number of solutions. And the difference here is that basically these equations are really just the same equation. If you multiply this equation by 2, it is literally that equation there. So here, the solutions are, so it's kind of funky the way you write the solutions, right? Because you can't say that every pair of x and y are solutions, because that's not true. It's that there's an infinite number of solutions and they live on this line. So you could say the solutions are the set containing all points x, y, such that 2x plus y equals 7. So when you have a matrix that is not invertible, either you have a situation like this where you have kind of parallel lines, right? These lines here, if you drew them, right, this would be y equal to negative 2x plus 7, this would be y equal to negative 2x plus 5. They would kind of look like that, where their intercepts were 7 and 5, and they never intersect, so that there's no solution, right? You're trying to solve these equations simultaneously. If they're parallel, you don't get any solutions. Whereas over here, these equations are not parallel lines, and solving them is like finding where two non-parallel lines intersect, which is going to look something like, I don't know, this and something else. Where do we intersect here? I don't know, something kind of crazy like this. like that maybe, right? We're finding we're at the one point of intersection of these two lines. If you have two lines that are parallel, then you're either going to have no intersections, no solutions, or you're going to have the lines being the same line, and you're going to have everything on the line as a solution. So you could have this situation, or you could have the situation where it's this line and then this line again, and oh, every point on the line is a solution. So, yeah. And again, I know we're out of time. It's kind of like saying the difference between solving 0x equal to 7, right? There's no solutions, versus solving 0x equal to 0. There's an infinite number of solutions. X can be anything. There, whatever you pick for X won't work. So that's kind of the difference. So when you're solving a system of equations, there's only 3 possibilities. One exact solution, if your matrix is invertible, or if your matrix is not invertible, either 0 solutions or an infinite number of solutions. But often, sometimes, something people will ask you is, can a system of equations have 2 solutions? And the answer is no. You can't have exactly 2 solutions. You can have infinite, but you can't have just 2.